And if you do brace it, one of the things you can run into is the manifold's going to move with heat. And if you have a brace that's too constrained, something's got to give. So a lot of times a brace that isn't expanding with the manifold can actually induce other stresses by trying to, stop that natural movement.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Matt from Morrison Fabrications. Now, Matt is a specialist fabricator who has dived really deep down the rabbit hole of exhaust manifold, or specifically turbo manifold design and development. And this is an area where I believe from my own experience there is a big lack of understanding or knowledge base around what you need to be looking for when you're choosing a turbo manifold. And I've been guilty of this in the past as well. I think most people tend to look at two different manifolds and think bigger must be better. Well, that's definitely not always the case. We talked to Matt about some really interesting back-to-back testing that he's performed on the Mitsubishi platform using two different runner types, and the results may actually really surprise you. On top of this, we dive deep into the topics of split pulse or divided versus undivided exhaust manifolds and turbo housings, the effect on spool, the effect on boost threshold, turbo response in general. We also dive into the topic of fabrication itself in terms of what materials we should be using for turbo manifold design, what welding techniques should be used. We talk about purging and we talk about gas lenses, just to name a few of these topics. So for anyone with an interest in fabrication and making sure you've got the best manifold possible for your turbo setup, this episode is full of information for you. Before we dive into the interview though, for those who are fresh to the HPA Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people about all manner of performance automotive topics. Namely, we cover EFI tuning, we cover performance engine building, wiring. Relevant to today's topic though, we actually do also cover fabrication, and we've got two courses there that may interest you. We've got our Motorsport Fabrication Fundamentals course, which teaches you, as its name suggests, the fabrication fundamentals relevant to a motorsport industry. And I know that a lot of enthusiasts kind of think that fabrication might be in the too hard basket. The reality is it is absolutely within the reach of anyone with a bit of an attention for detail and a little bit of patience. That course teaches you the fundamental skills that every motorsport fabricator needs. You'll learn about the tools required as well. If you want to go a little bit further, we also have our practical motorsport TIG welding course, and TIG is really synonymous with motorsport fabrication. It gives you the most amount of control over the finished weld. It puts the smallest amount of heat into your welds as well, really critical when you're dealing with some of the materials we come across in motorsport like chromoly. It also gives you the ability to weld a really wide variety of materials, namely mild steel, stainless steel, even titanium, as well as non-ferrous materials such as aluminium. This particular course will teach you everything you need to know about choosing, setting up your particular TIG welder, and you'll also learn a simple step-by-step process that you can apply irrespective of the material you're interested in welding. I'll put a link in the show notes to both of those courses, and as a podcast listener, you can use the coupon code podcast75. That'll get you $75 off the purchase of your very first HPA course. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Matt. Thanks for joining us today. And as we usually do, let's get stuck in by finding out a little bit about your background. So you are a fabricator. We're going to dive into that. But how did you initially get sort of interested and involved in the automotive scene?
I guess it started out when I was a kid. I always had a fascination with anything mechanical or engine specifically. I would spend some weekends at my dad's workshop building like little Stirling engines or steam engines or compressed air engines of different kinds. Once I got my driver's license, that shifted over to cars. My first all-wheel drive turbo Talon, being the first car I took to the track with had a manual boost controller at 15 psi and a 3-inch exhaust. I went in kind of expecting like a low 15 or a high 14. First pass was a 13.6. I was so happy and thinking, these are like Buick Grand National times. That really got me hooked for, tracking future progress at the drag strip.
That Talon Eclipse, that was sort of one of the star performers in the Mitsubishi / DSM market. I mean, I followed that particular platform quite thoroughly from New Zealand, which was why I got involved in the Mitsubishi platform, albeit here in New Zealand with the Evo. And I mean, obviously at the time, John Shepherd, well known for his 7-second Eclipse as well, which I think is one that anyone in that DSM market was sort of looking up to in awe, correct?
Yeah, that was actually right around the same time that he was first going into the sevens. So, I had that in my MySpace page and was pretty enthusiastic having the same make and model of his.
In terms of modifications on the car, you mentioned you've got a boost controller and a 3-inch exhaust. So, is this the start, particularly with the exhaust at least, with your fabrication, your sort of journey and down that path, or was that how the car was purchased?
Honestly, that's how the car came. It wasn't until later in like 2010 where I decided to go to a junkyard, get an HX35 off a 2000 Dodge Ram diesel truck. And, it wasn't that uncommon at the time for people to use they made a bolt-on turbine housing so you could bolt that turbo up to a stock manifold and run it. Or, people would have like a standard T3 manifold and then use that factory divided T3 turbine housing. But no one had really tried the stock divided T3 housing with a divided T3 manifold. And I don't think anyone made it at the time. So, that was a good excuse to build my first turbo manifold. So I bought the head flange, some mild steel weld L's, wastegate, and I had my dad's MIG welder in the garage and just got to it. I was actually able to get away with a single wastegate by, in the wastegate revisions, keeping them divided all the way up to the base of that wastegate valve. It was actually profiled to the valve face. That way there's no crosstalk. Actually verified that by doing some boost threshold testing first before the wastegate revisions were on, and then afterwards to make sure that RPM, stayed the same for when it could reach whatever boost level. And, the setup worked surprisingly well. Shortly thereafter, it's a 54 millimeter HX35 for reference. Shortly thereafter, back at the track, it ran a 10.9 on street tires with the 5-speed. Got a little bit further in, but I actually switched to an automatic, which was a really nice change of pace and was really fun to work with the stock torque converter, which was a big question because, again, at that time, anything bigger than a 16G, it was really hard to get it up on the stall and actually build boost so you can launch it. And it was able to get up on the stall and actually build as much boost, 30 PSI plus, against that stock converter without much issue.
I don't want to go too far down this path because we are here to talk about fabrication, exhaust manifolds, and all of that good stuff, and we will get to that. But obviously, I have a background in Mitsubishi drag racing, so I can't go past this auto trans. So let's talk about that briefly. I mean, anyone who has drag raced DSM or Evo platform, the transmission, particularly in those earlier models, was always the Achilles heel. We ran a stock transmission up to the point my car was running sort of mid to high nines, and we were braking fourth gear with reasonable sort of consistency. Not something you want to be consistent at. Gets quite expensive. So we went down the PPG 4-speed dog engagement gear set route, which a lot of people have. The auto transmission obviously is another popular solution. I mean, we look at a lot of the fastest drag cars out there, and the auto trans has become the choice. But when you're stuck with OE parts from Mitsubishi, sometimes that's not so easy. So, first of all, can you just really briefly talk to us about what needed to be done to that auto trans in order to make it support the power you were making? And then we'll talk a little bit about what you were talking about with the stall speed.
Yeah, so on that particular transmission at that time, it was as simple as, I think it was like a standard shift kit, which just increased the line pressures. And then you do what was called a blue wire mod that would make it so it was at full line pressure when you needed to make those shifts, the frictions last. And honestly, that was about it. I guess, too, there was the welded center differential, which really just helped, keep power going to all the wheels instead of just the front spinning like a fuse. when it got overloaded. But it was honestly really basic, and like at the time, like not many people were doing it, so you could find them used for like $50. But those times are gone. But
yeah, those times have gone with, unfortunately, the broad range of parts, sadly, but that's it is what it is. And just again, I won't dwell too much more on this, but just what you mentioned with the torque converter, this is a problem with a small capacity engine with a bigger turbocharger, although arguably the turbo you're running, definitely not massive for the 4G platform, but with a manual transmission, we disengage the clutch or put the clutch in, and put it in first gear, and we use a two-step launch control. Basically, we can build almost as much boost as we want, but with a torque converter, you actually load it up, and this can be problematic with these bigger turbochargers to actually build sufficient boost because the engine RPM is held down too low where the turbo is not really making boost. And it's the simplest way of explaining it. Is that sort of what you're talking about there?
Yeah, that's the first hurdle, is just getting it to push hard enough against the converter to build the boost. The problem that I actually ended up having was it could build whatever boost it wanted, and the key ended up being bringing that RPM down and playing with the timing values in order to cut the torque but still increase the amount of boost, so you could hold the car back at the line, not shock the tires too hard, and then by retarding the timing and keeping the boost up, but as soon as you let off the brake, it would trigger all the timing back in. You'd already have the boost, so there's no delay between letting off the brake and applying as much power as possible, and finagling with at what point that is to be at the traction limit.
Yeah, absolutely. I mean, we don't want to just leave the line with all four tires going up in smoke. That doesn't make for a good 60-foot. All right, well, let's get back onto the journey that you were taking back here. So, I mean, it sounds like that was one of your first experiences in fabrication. You said you're using your dad's MIG there. Did you have any formal qualifications, or have you had any formal qualifications with fabrication and welding, or is this all self-taught?
It's all self-taught. Lucky enough to have a lot of experience with a lot of local DSMers at the time. I was able to be part of their build and really get a feel for a lot of different types of setups instead of just my own, and gain a lot of hands-on experience there. And forums were huge too, or YouTube for welding honestly was a big help. And then Samantha, my wife, had been welding and had professional training, so she was a big help there as well.
I mean, clearly you've a case study here that formal qualifications in welding are not essential for automotive fabrication. If someone was looking at a career path to do something similar to you, would you now, with the benefit of hindsight, recommend some formal training, or is it just not necessary?
I think it really depends what we're doing. It's fairly specialized, but if you were to, want to have a really broad range and want to be able to tackle anything that comes at you, it's going to be different. You're probably going to want a more formal education, but we had a jump start because when Ron Shearer was doing the DSM Evo thing, and when he stopped doing it and broke away from the Evo and DSMs, he reached out to Samantha, and we pulled the trigger on that to take over that side of things, and then we got the benefit of all his knowledge and trial and error and tips and tricks and all that. So without that, I think it would have been much different.
Okay, so that sounds like it fast-tracked your knowledge base. At what point did you decide, or had you already decided that a fabrication business was going to be what you wanted to start?
I guess it was once Ron reached out, and Samantha and I had conversations and just wanted to make it happen. It's something she'd always wanted, and something that, I said that I'd never make another turbo manifold again after the other one being pretty much hand tools and a MIG welder, but we made it happen, and pretty much took the first year, honestly, of just really diving in and getting the process down before offering anything, which I think was huge too.
What are the sort of challenges or fears, I guess, would be the other aspect in terms of taking that plunge and starting a business from scratch? Obviously, a lot of people listening could be in the same situation where maybe they've got a day job, they've got a passion and a skill that they're good at, and they're sort of trying to decide if they take that leap of faith and give it a go. What was that situation like for you? Was it a scary process to sort of just go into this, boots and all?
Oh, for sure. I think we were lucky though, where we had plenty of like side jobs to take on at the time, and we still had full time or turning into part time jobs to kind of keep things rolling in the background. Where just taking that extra time to just get acclimated with the business and what's ahead of us. I don't know. It's gonna be different for everybody, and trying to work it in. It's hard to speak outside of that.
Sure. Of course, yeah. Every situation is going to be different, but I know that fear is definitely something that holds a lot of people back. In terms of building the business and the customer base, how did you go about that? Was it already based off? It sounds like you had a reputation there in the DSM scene. What was the process of attracting customers?
Yeah, I had I guess a presence on the forums, at least on the DSM side of things, and then Ron was a big part of that as far as reaching into the Evo side of things, and just starting to do it, just starting to offer those products and develop. And Evo M was a part of it too. I don't know, it just kind of happened, I guess, where once you start rolling and offering it, it just snowballs from there. And now we're grateful enough to be just almost overwhelmed with the business.
Give us a high-level view of what the business looks like today. Is it still just solely you and Samantha, your wife, or have you got other staff? What's your facility look like?
Just Samantha and I. The facility is not impressive by any means. It's just essentially still out of a detached garage, but it works out really well. Kind of always been trying to do a lot with a little.
Is there a consideration to grow the business in terms of adding additional staff to keep up with demand, or are you just managing the demand so that it can be run with you and Samantha?
More so managing it so it can be run with Samantha and I, because we really want to have a strong hold on the quality of the product. And there's pros and cons to having other people and employees, but right now, ideal situation is keeping it Samantha and I. And I think that's been working out and will work out in the future as well.
Okay. I mean, obviously, just being two people, that's going to limit the scale of what you can do. Can you give us maybe an idea in terms of the number of manifolds you're producing? Maybe what's that look like? How long does a manifold take you? How many you're punching out, sort of in a month or even a year? Just in broad terms.
I can kind of speak to like a week. It depends. If it's a complete hot part setup or if there's any design work that has to be done. Typically, like, I don't know, around 3 complete setups per week, but it can depend on what else is going on at the time too.
Yeah, I guess not all of them are going to be as straightforward as every single one. So yeah,
for sure.
Just getting a broad idea here. All right, let's move into some of the specifics of manifold design, and I think, when it comes particularly to turbo manifold design, this is an area that's maybe a little bit of a black art, a little bit of mystery around it, a lack of knowledge compared to the likes of maybe a naturally aspirated exhaust manifold, where there's some calculations you can go through, and there's pretty good formulation in terms of runner size, runner length, step primaries, etc., to get a result. And I haven't seen that so much in the turbo manifold design industry. Most people are just buying whatever they see that they like off the shelf from a range of manufacturers, putting it on the car, and obviously if it works, happy days, but there's not a lot of back-to-back testing. So I wanted to dive into some of this because I know that you do go a little bit deeper than most with the science behind it, and also back-to-back testing, which is interesting. So maybe if we start with one of the intricacies of the 4G63, but it's not solely the 4G63, which is the flange shape, in that the exhaust runner is not round, it's oval. Obviously, that creates a bit of an issue because the tube that we use for fabricating an exhaust manifold comes round. Variety of ways of dealing with this shape transition. So talk to us about what the options are, and maybe pros and cons, what you've found.
The most straightforward option would be the flange that is CNC machined to do the transition in the flange itself, to go from that oval, and then you have the machining so it in that 3/8 inch or 7/16 or half inch, whatever, to the round, that ends up with fairly abrupt transitions. And you actually have to offset the pipe down in order to have hardware access for the nut and bolt, or nut and stud, I should say, just above it. The other option is what we use, which is an oval flange. And what we'll do is we'll shape the runner to the port. And what happens is you end up with a great transition just by the act of forming that runner to an oval. And then again, that oval is, shorter in height. So you have that hardware access. But I think more importantly, it's that transition, especially right off the exhaust port. And it opens up a lot of design possibilities. We actually cut apart a lot of different cylinder heads to see the cross section of the exhaust, to make sure that each of the transitions that we needed off the port, whether we needed a bend going up, cut everything in half and make sure that it turned out to be a really fantastic transition by forming the runner. So you have, instead of like a half inch of quick transition, you have like an inch and a half or more of gradual transition from the oval to the round runner. And something we do a lot too is, stepping down a little bit as far as the runner size versus the port cross-sectional area, where we can do all that really smoothly. And I think that can be key as far as really taking advantage of when you use a runner that is smaller than what I might say is a typically oversized, for many of the application, exhaust port.
Okay. There's a few elements that you just talked about there that I want to just sort of go back and unpack in a bit more detail. Obviously, we don't have the benefit of visuals here. I think probably most people listening could understand what we're talking about here, but transitioning from that oval to the round shape, using purely the thickness of the exhaust manifold flange, be that half inch or 3/8, whatever it may be, that by definition must create quite an abrupt change in profile. And I mean, I'm not a head porter, but just looking at that abrupt transition, it reeks of, this is not going to be a great thing for flow. I also will link to one of your technical articles in the show notes if people want to see those cutaway cross sections, because I found that really interesting. So if people want to have a look at that, they can do it. In terms of the oval flange with the transition that you're talking about there in the pipe, so transitioning from the oval shape to the round through the pipe, there's got to be a limit as well, because particularly if you're looking at maybe a stock location turbocharger, you're working with a really reasonably tight confines in terms of where that manifold can run. You're kind of constrained by where the turbo is. So does that, by definition, then kind of limit how smoothly you can transition, because often you may have to have a bend essentially straight off that manifold flange?
Yeah, so it really comes into play for some of our top mount DSM manifolds, where you have to bend the runner down immediately off the flange in order to clear the compressor cover, which is right there. And what that allows you to do is pretty much butt that bend. And on our flanges too, the runner plunges through or sticks through the inside of the flange. So you can actually initiate that bend pretty much at the port flange interface where the gasket is, and initiate that bend there, and tuck that runner in that much closer, but still not compromise the actual bend. Not try to do all that transition all at once. You can just have it naturally falls out where you smash down that bend. That's not a good word to use, but you form that bend to the port, and then it just kind of all does it for you essentially. It just falls out that way.
Yeah, it makes sense. And the other thing I'm glad you mentioned there is the access to the hardware. And this is something that's really easy to overlook. And I mean, not strictly limited to Mitsubishi manifolds, but I've installed my fair share of fabricated aftermarket exhaust manifolds where seemingly little to no thought has actually been placed into how the hell the mechanic or tech is going to actually install the thing. And my pet hate here is where essentially the weld bead is butted hard to the outside diameter of the nut, or the runner itself, to the point where you're forced to use the open end of a ring spanner, which I mean is never ideal. You can't really apply the torque to the hardware that you need to. You risk rounding off the nuts. It's just ugly. So I'm glad that you mentioned that you obviously think that sort of stuff through to make it easy for the manifolds to actually be installed and removed. I wish more people did that. Now, in terms of results, are you able to give us a sense of a back-to-back on just the difference in that transition, where, transitioning just through the thickness of the flange versus doing a nice tapered transition? Have you ever done back-to-backs on just that element?
I really wish I could say that we did, but we have not. We have some other things to back up that, it's probably a really good idea that, energy at the port is going to be really important, but we haven't done that dedicated back-to-back test to be able to speak to that.
I mean, just looking at it from a common sense perspective, it does make sense to me that the taper would offer an advantage over such a short transition. But yeah, I mean, obviously just doing sometimes a single back-to-back test on something so specific can be quite tricky. Now, the other thing, and I can't remember where I read this. I really wish I could remember the resource that I used for this, but I have in the back of my mind that a fairly well-respected turbocharging specialist recommended with fabricated manifolds that an offset of the primary at the exhaust flange, whereby the bottom of the tube is flush with the bottom of the exhaust port, but the top of the tube is actually offset slightly above the port. And what that creates essentially is a step at the top of the flange. And that was beneficial, my understanding or recollection was, for reversion pulsing of the exhaust flow. Can you speak to this? Is there any sort of weight to this, or is this kind of urban myth?
The idea is really important. It'd be, I think, what they would refer to as a reversion dam. And the idea was to let the exhaust flow out, but if there was any reversion where the exhaust tried to change direction, it would run into that little step or that wall there. I think there are different ways around it where you want to keep the port velocity high, keep the exhaust moving, don't give it a reason to stop. So you can avoid reversion by creating let the exhaust keep moving and then create a depression in the cylinder at the end of the exhaust stroke, and then give somewhere where that intake air charge can fill in. I don't want to get too far into that right now, but basically keep the exhaust flow moving instead of trying to create a little air dam to do that. Instead, just keep it a smooth transition.
And there's practical implications of that as well. And we've just talked about the ability to get to the hardware, and the location, of course, of the studs on the 4G63 directly above the runner is obviously going to make any offset in that direction very difficult, correct?
Yeah. I mean, it can be beneficial for moving it down for the hardware access, but I still much prefer the oval flange, and then some of the things that we've seen, at least in our other back-to-back testing, that seem to prove that out as well.
The next question is runner size, and there's as many opinions on this pretty much as there are people offering them. No real firm sort of answers that I've seen, and I'm interested in your take, particularly again in the technical resources on your website. You've actually done a back-to-back test, which was actually a little bit of an eye-opener for me. So talk to us about the theory around runner size, what you need to consider, and where, from your experience, you want to be.
So our first experience with it was back in 2010. That first turbo manifold that I did use that smaller runner size, and I wish I could speak to what led me to do that, but either way, that's what I used. And I think that was part of the reason why it had such great results as far as transient response and boost threshold and all those things. But typically people will use a runner size that matches the exhaust port cross-sectional area, which would be, I guess, what we've tended to call the large runner, which is 1.5 inch national pipe size, which is like 1 7/8 comparable or so for tube size. Anyway, we did that back-to-back test to kind of prove out where that crossover point would be for this smaller runner to the larger runner, see which is a better match. It was a 62 millimeter turbo setup. We kind of went into it thinking that it's probably going to make the smaller runner look bad, because it's going to be a 700 wheel horsepower or so setup. It feels weird going down to a smaller runner size than the, port size. But, we've seen a lot of real world evidence there. The setup seems to actually work really well, and really wanted to see what those graphs look like overlaid. And what we did find was that through varying boost levels, surprisingly, the small runner, it spooled sooner, which wasn't a huge surprise, but it also made more power per PSI throughout the entire rev range on that setup, which was a divided T4 62 millimeter Borg Warner.
Looking at those dyno results again, obviously we can't show them, but I mean, that was up to, I think, 715 wheel horsepower. And I mean, obviously, much like yourself, I expected the small runner to provide maybe an increase in boost threshold, or an improvement, I should say, in boost threshold, and probably fall away in the top end, and worse so as the boost increased. But pretty much in every situation, the small runner just outperformed the big runner, correct?
Yeah, in that setup, yes, which was really surprising to us as well. We expected it to, higher RPM taper off or higher boost levels for, something to give where the large runner starts to shine. But in that case, surprisingly, it did not.
Now, obviously, that's not to say that the small runner is going to be the perfect solution for every application. I mean, I'm guessing at some point, maybe once you get north of 800, 900, maybe 1,000 wheel horsepower, particularly with larger turbochargers, perhaps at that point, I would expect at that point, the big runner is going to come into its own and the small runner will become a restriction. Is that your expectation as well?
Oh, absolutely. Absolutely. It was surprising at that power level where, we still hadn't reached that crossover point. That's not to say that different setups with open setup perhaps, or, a lot of different variables to say that a 700 wheel horsepower setup couldn't benefit from the large runner. But for that one, the small was a pretty easy choice for the customer.
And I think this also speaks to a really common trend when people are shopping for aftermarket parts. And this goes for almost everything. Turbo manifolds, turbochargers themselves, maybe intercooler plumbing, and camshafts would be another key one. It's really easy to get suckered into the bigger is better mentality. But it's really so critical. I see this mistake being made so many times. You really need to focus on the application, and putting the biggest parts on a street car are probably going to, in most instances, actually make the car slower on the street and ruin the experience and make it worse compared to, obviously for an all-out drag application, yeah, fine, have at it. That's probably what you're going to need to get your results. But very important to actually choose parts that are sized appropriately for your application. And obviously there the turbo manifold comes into that as well. As well as the runner size, we also have runner length. And I'm interested in your take on this. I don't see it being as critical with turbocharged engines as with naturally aspirated engines, but what's the best solution here? Are we looking for as short a runner as possible to maintain the exhaust gas energy and get it into the turbine wheel as quickly as possible with as higher exhaust gas velocity, energy, heat, etc., or are the benefits to going longer?
Typically, you want to keep them shorter. Longer, you will usually strive to go for a wave tuning effect. The problem is, to get that wave tuning effect in a usable RPM range, you have to have runners that are extremely long, like 2 feet or longer, in order to even get it down to like 9,500 RPM or so. So the wave tuning effects you can kind of ignore for most setups that are going to package in a typical DSM or Evo engine bay. Equal length is another thing that comes up a lot too. Something you don't necessarily want to go way out of your way and make compromises to get equal length, but you do want to avoid any errant tuning effects that could cause different cylinders to have different tuning points and then have different fueling requirements and then have unequal cylinder to cylinder AFR essentially. So obviously that's not a great thing. And then length in general, we started to run across some things where, if you think about it more as far as negative cylinder to cylinder interference, certain setups, specifically open setups, you will have one cylinder is at the end of the exhaust stroke with the exhaust valve open. You have another cylinder that's just starting the blowdown phase where the exhaust valve opens. If that blowdown phase can travel down one runner, up the next, and then into that end of the exhaust stroke another, and it could possibly blow a bunch of exhaust into that cylinder, especially during the overlap phase, and then reduce again the volumetric efficiency, and essentially will make the engine act smaller at that point too, because volumetric efficiency is really analogous to the engine displacement. And longer runners typically make it so you can get out of that range where you'll have that negative cylinder to cylinder interference sooner, because as RPM goes up, you cut off the time for that pulse to make it to the other cylinder, and at the same time, longer runners make it take more time.
Okay, so I mean, if I sort of paraphrase what you're saying there, the longer runner can help reduce that, exhaust gas making its way back into another cylinder on overlap, reducing the VE of the engine. But there's a practical element there in terms of packaging those longer runners in the average engine bay gets to be tricky.
Yeah, as far as like looking for a wave tuning effect, it's going to get tricky, but a slightly longer runner can still have that same benefit of, lowering the RPM range, where you can get out of that negative cylinder to cylinder interference effect sooner, specifically for an open setup. And then that kind of leads into where divided setups tend to, from what we see, have a longer lever for how they actually give that better response and power per PSI, et cetera.
We'll jump into this divided versus open in a moment. I mean, nothing particularly new there, but we'll discuss it. Before we do that, you mentioned the runner length, sort of trying to equalize them cylinder to cylinder. Now, in the naturally aspirated world, that becomes quite a big deal. You sort of just alluded to the fact that it's a little less critical with the turbo manifold, but again, the installation really drives a lot of the decisions. But when you're sort of looking at designing a manifold, what kind of length variation are you aiming for across the four cylinders?
Sometimes we can get within like almost exact, or it's fine too if it's within a few percent. It's not something to make compromises. If you can get it really close and it's not going to change anything else, then do it. But you don't want to go in the wrong direction where it's not going to make that big of a difference for that given setup, especially when it's less than that critical length where you're not going to have any wave tuning effects to speak of anyway.
Yeah, okay. Now, and I think it's just important because people overlook the cylinder-to-cylinder variation that we see. I mean, the main reason for this is, of course, 99% of people are tuning off a single lambda sensor that's fitted post-turbo, and that's absolutely normal. And it's not until you actually have the benefit of individual cylinder exhaust gas temperature sensors, or even better, individual cylinder lambda sensors, where you actually start to get a little bit more insight into the variations we see. And I mean, understandably, there's a range of elements that kind of build up to cause these variations: inlet manifold design, cylinder head porting, and then, as you've said there, the exhaust manifold also can play a part. So it's a culmination of all of those things. But in an average street car, maybe moderately powerful, the variations might not be sufficient to actually cause any concern. But once you start pushing those power levels up and your tuning becomes a little bit more on the edge of the envelope, all of a sudden a variation of fueling of a few percent on one cylinder, that often can be enough to actually cause some problems. So it is definitely something to consider. Moving on to the divided versus open setup. So I'm going to assume that most people listening probably have heard those terms before and have an understanding, but maybe for those who haven't, could you give us a high-level view of what those terms actually represent, what they mean? Okay,
so I'll speak to a four-cylinder application because that's what I'm got most front of mind. That's where you're going to pair the center two cylinders and the outer two cylinders, and then have those cylinders enter into a common turbine housing that has a split flange. And you do that in order to pretty much shield those cylinders from the other ones. On one hand, you are creating more ordered exhaust pulses into that turbine housing. I've heard that can increase some of the turbine efficiency. I can't speak to that as much, but the fact that you are shielding off those cylinders in a way where you're not having one cylinder in overlap and another cylinder starting its exhaust phase and then pushing exhaust into that cylinder during overlap, you really have to look back at the engine and how the engine behaves and how it responds to those Again, negative cylinder to cylinder interference. I think that's the biggest lever for explaining, why a divided setup tends to, especially like low mid-range RPM, tends to get those volumetric efficiency increases and generate more mass airflow through the turbo sooner. And it also tends to, at the lower RPMs, create more power per PSI.
I mean, all other things being equal, which is always challenging when we're talking about comparing an open to a divided setup, boost response is going to be superior in terms of bringing the turbocharger onto boost earlier, bringing that boost threshold down lower in the RPM, correct?
Yeah, it does get tricky. You'll be hard-pressed to find a back-to-back exact test because inherently, since each exhaust pulse on the divided setup only sees half of the turbine AR at a time, you have to upsize that overall turbine AR ratio, typically by like 25 or 30%. And then, there's other factors that we can get into for, what divided setups tend to be less sensitive to camshaft overlap. So you can start to get away with that. So it's hard to have a exact apples to apples comparison when you do that. There's so many other variables that come into play. Things you can take advantage of and advantage of too with the open housings as well.
Yeah, absolutely. Yeah, as I mentioned, very, very hard to do that that sort of, all other things being equal test. But I think we've covered that off. One of the complexities with a split pulse or divided setup is around the wastegating. I want to sort of talk a little about the wastegating in general. You also have already mentioned that with the setup you did for your DSM. So what we see these days is most of the fabricated manifolds for a split pulse design generally have sort of tended towards incorporating an individual smaller wastegate per side of the turbine housing, essentially. So one element is it's important to get the split pulse effect, the divided effect in its full, to get all of those advantages, that we actually maintain that all the way down to the turbine wheel. So makes it a little bit tricky if you just basically bored a hole through the collector of a divided manifold and then just welded a single pipe coming off that to your wastegate. That ruins that effect, correct?
Yeah, any crosstalk is going to have actually a significant effect on essentially making it act more like an open setup than a divided setup. We'd actually done some random testing where we took a setup that was divided up to the wastegate valve. We blocked off the wastegate outlet, and then we took out the springs, so that would allow crosstalk between that divider, where that divider then allowed the exhaust to travel in between. It wasn't even that much of an opening, but between the two different setups, there was a 8 or 9% difference in boost threshold RPM. So the one where it allowed it to crosstalk, it took, I don't remember the exact, but it was 8 or 9% difference in boost threshold RPM, richened up about half an AFR, so it lost engine VE. And honestly, driving around just to do the testing, you could tell it was more sluggish. So I mean, it was a pretty basic back-to-back test, and it showed that even that little bit, and a lot of manifolds you'll see where they don't completely go up to partition off up to the valve itself, where it just ends at the flange, or there's no divider in it whatsoever. It can still be beneficial, but it doesn't take much in order to allow that crosstalk to have those cylinders get that interference.
Okay, so clearly incorporating two separate wastegates, one off each side, completely eliminates that crosstalk as you've referred to it. So, yep, I get that. Nice and simple solution as well from a fabrication perspective. But from the end user perspective, a little bit more complexity in terms of, well, now we have to buy two external wastegates. We've got to plumb two external wastegates. If we are plumbing them back into the exhaust, that becomes a little bit trickier as well. Just a little bit more involved in that. From a fabrication perspective, though, I'm guessing much simpler and cleaner than potentially quite a tricky solution, getting a divider into that wastegate feed to a single wastegate and getting it nicely profiled so it essentially sits against the valve when the wastegate is closed. Is that sort of the balance between those two options?
Yeah, honestly, it's a nightmare. Even the weld order to make sure you can get everything to weld every part. Really, it just makes so much more sense to use two wastegates. In the end, the labor well offsets the cost of another wastegate.
I just wanted to really dive into why that is what we see with these divided manifolds and what the potential alternative may be. Now, before we sort of actually started recording this interview, we had a quick chat, and you mentioned drive pressure or exhaust manifold pressure, exhaust manifold back pressure, and that its relevance on the performance of the engine as a whole. And I wanted to dive into this because this is a topic that those new to turbocharging probably don't initially consider. Obviously, the key element that we are measuring and understanding is boost pressure, and the exhaust manifold pressure, because we don't normally monitor it, is something we don't think about. But as we sort of get more into optimizing the turbo system, measuring that exhaust back pressure and also comparing the relationship between inlet manifold pressure to exhaust back pressure, it actually becomes quite an important topic. So can you talk to us a little bit about that, what you've found?
Oh, absolutely. I think that's something that's definitely not talked about enough, where you want to have a favorable boost pressure to drive pressure ratio, especially during that overlap phase, which is going to dictate which direction things go. If it's favorable, you're going to have intake air charge going into the cylinder and exhaust going out. When it's highly unfavorable, you're going to have exhaust backing up into the cylinder, or even worse, going into the intake manifold. And the exhaust stroke is just before the intake stroke. So if you leave any exhaust behind, it travels back and takes a ride into the intake stroke. It takes up space. It's also hot exhaust gas, which is another conversation, but it takes up space that could otherwise be filled by fresh intake air charge. That has a direct impact on engine volumetric efficiency. And when you look at it that way, it makes a lot of sense why engine volumetric efficiency changes are almost identical to, you can think of it like an engine displacement change. It literally makes the engine act smaller.
There is, of course, a balancing act here that we need to consider, because the exhaust back pressure, obviously there's a bunch of elements here, so I don't want to try and oversimplify things, but if we are just looking at the EMAP, the higher that EMAP, essentially it helps drive the turbocharger. So what we tend to see, and again, trying to keep this relatively simple at a high level, if we looked at the relationship between inlet manifold pressure and exhaust back pressure on maybe a factory turbocharged car, we might see somewhere in the order of 2 to 1, maybe even higher. And by that I mean, if we've got 15 psi of inlet manifold pressure, our boost pressure, we may see 30 psi or more of exhaust back pressure. And that's done because the manufacturer is really interested in getting good boost response. They want a low boost threshold, the boost coming in low in the RPM, and good sort of transition onto boost if we're higher in the RPM. So that drives the turbo really, really quickly. But of course, it tends to choke or strangle the exhaust flow at higher RPM. If we look at the flip side of this, and I'll take my drag car for an example, and that ran, it's a pretty old school turbo now, the old HKS T51R SPL turbo, and on that at about 40 odd PSI of inlet manifold pressure, we still weren't exceeding the inlet manifold pressure in the exhaust. So 40 PSI in the inlet, I can't remember the specifics, maybe we had 35 PSI in the exhaust. So that relationship works exceptionally well because we've essentially got less exhaust gas restriction. Works really well for high RPM performance and power, but obviously the limit there is the boost response. The low RPM performance is terrible. Works fine for a drag application. So I just wanted to give those sort of two sort of extremes of the situation. The other thing that I found as well was that this plays into your camshaft selection, and it's pretty much what you're talking about there in terms of the exhaust gas on overlap making its way back into the cylinder. If you run a cam that's really aggressive with a lot of overlap with a small turbocharger with a high exhaust manifold back pressure, that's going to tend to exaggerate that effect, reducing your VE, compared to running that same large aggressive cam, lots of overlap on a turbo where the EMAP is below IMAP. Is that sort of been your experience as well?
Absolutely. Just in general, engines are pretty sensitive to any exhaust back pressure in relation to negative VE effects or losing volumetric efficiency, and even more so for camshafts with more overlap, longer duration. they're much more sensitive to it. There's much more opportunity for that unfavorable flow to end up where it should not.
So again, it just comes down to really understanding the setup that you've got as a whole, as opposed to sort of cherry picking individual parts that aren't going to work together, because that camshaft versus turbocharger sizing is such a critical element. In another instance, as I referred to earlier, where just choosing the biggest, baddest part on a cam manufacturer's part list is probably not going to give you your desired result. Now, I know it's really very difficult to come up with generalizations or rules, but have you got any guides from what you've seen, relationships between IMAP and EMAP that work well for maybe a street-driven application versus maybe a road race application versus drag?
Specific ones, I mean, anything below 1-to-1 is a really efficient setup, but typically you might be leaving some power under the curve available. Sometimes 2 or 3-to-1 back pressure to intake pressure setups can be a blast because, maxing out of turbos, it can be a pretty good time. But I think that is kind of where what a turbo manifold can do comes into play, where you start to realize that not every part of the exhaust phase is as sensitive to that drive pressure. So you can have that average drive pressure. The exhaust is a pulse, and the turbo manifold will change the peaks and the valleys and the shape of that pulse and where it comes back into the cylinder. So you can have the necessary drive pressure to drive the turbine. And if you can have the exhaust manifold that makes sure at the end of the exhaust stroke and during that overlap phase that it can still have a trough or a depression or pull down on the cylinder and keep the exhaust out, you can shield the engine from that higher back pressure. Even though you're still generating it every other time and getting that average, you can shield essentially the engine from it and then allow it to have at that moment still have a favorable boost to back pressure ratio and still have it, exhaust move in the direction it should, even though you're still working with that back pressure.
Yeah. In terms of what a customer could expect, and again, this is a really tricky one because there's so many variations here, but I'm just interested, going from, let's say, a factory cast manifold on that Mitsubishi platform to one of your stock location replacement tubular fabricated manifolds, same turbo, essentially every other thing being equal. What would you be expecting as a result? What are we going to see? Are we going to see an improvement in that boost response, boost threshold? Are we going to see more power per PSI as a result of just what you've been talking about? And if so, what sort of magnitude?
So the main thing that we've seen is power per PSI, and that's really analogous to the volumetric efficiency, and then relating that back to volumetric efficiency being really analogous to engine displacement. It'll make more power PSI. Smaller turbos where it's going to be limited by the turbo itself and you're going to get that compressor limit. It's not going to add power there. I think that's really important to say that, if it, even the back-to-back test, if it picks up X horsepower, once you're at that compressor limit, like airflow is the main lever for, how much power is able to be made outside of, little details with timing and what else you can get away with. But that's really the limiting equalizer is the compressor flow. But what it will allow you to do is get to that compressor limit requiring less boost. And also you can start to realize that it does that because it has, in many cases, less exhaust gas remaining in the cylinder. So therefore, you don't have to try to overcompensate with more boost to shove that intake air charge next to that exhaust gas in order to get that same airflow with those RPMs.
Yeah, that makes sense.
I mean, obviously there's a lot of other things you can take advantage of as far as, opening that tuning window and playing with other things. But as far as a back-to-back test or, a lot of the conditions that we test in, like the compressor flow is the limit, but it just changes the PSI that it takes to reach that limit. It takes less boost to reach that limit.
I want to just circle back. We've talked a little bit about wastegates, but what I want to also cover off is the importance of how the wastegate integrates. So here we could be talking about open or divided. It doesn't matter. I'm not talking about the twin wastegate element. I'm talking more about how smoothly the flow from the exhaust port can make its way into the wastegate. So, I liken exhaust gas to being pretty lazy, and I've seen issues where the way the wastegate integrates off the collector is not that nice, that it's sort of coming off at a 90-degree angle, or worst case, it's actually sort of almost going, the exhaust gas has to go back on itself. So yeah, what's the issues with this around boost control, and what are you trying to achieve with how you're integrating the wastegates into your manifolds?
You always want to have a nice angle of entry where you can. On our higher pressure ratio setups that we often work with, you actually can get away with less than ideal placement, as long as that end result controls boost within that given target boost range. So, the wastegate's function is to modulate the amount of dry pressure by bleeding that off, which then controls boost pressure. The dry pressure required for that given boost is dictated by the rest of the setup. So the wastegate or even the angle of entry isn't going to affect that. So essentially, if the end result is you can control boost within the target boost range, which on a lot of our stuff is, 20 or 30 or higher PSI, even if it doesn't have a perfect angle of entry, which honestly on a lot of stuff it's really good, but on the setups where packaging doesn't allow it, you're not going to find a benefit by changing it to a better entry or putting a larger wastegate on, because, it's just not going to use as much of the wastegate, or it's not going to open the wastegate as far. It all comes down to just modulating that dry pressure to control boost in the target boost range. You may not be able to go down to like stock boost levels, but if you're above that, it really doesn't matter, I guess, is the ultimate thing. If it works within that range, there's no benefit to be had. It's not going to change that ratio of dry pressure to boost pressure or anything like that. That's dictated by other things.
Yeah, and I think what you sort of touched on there, that's really important to sort of consider, is that sometimes your installation will be compromised by, what you have to work with. I mean, we're dealing sometimes with very tight engine bays, and we may not be able to locate the wastegate in what would be considered, the quote unquote optimal angle and location. So sometimes that may need to be compromised. And again, as you say, if it controls boost within your chosen range, well, that's fine. What I'll add is, what I see with really poorly integrated wastegates, and obviously I'm not talking about what you're producing here, but subpar manifolds where I have had on the dyno in the past, and what you'll find is as the RPM increases, the exhaust gas just can't make its way cleanly out of the wastegate, and you sort of end up seeing this sort of boost curve that just sort of starts to go exponential at higher RPM. And in worst case scenario, you could hold that wastegate completely open and the boost is still going to exceed your target. So obviously that's not going to be a reliable setup. You can't run like that. So there's levels to this. My experience, again, the smoother that integration of the wastegate, the flatter generally you're going to get a boost curve, which can be an advantage. Not insurmountable with programmable ECUs with good boost control strategies, but that's one of the elements that I do tend to see there. Now, I want to move on and talk a little bit about the materials that you're using for these manifolds. There's a variety of different materials we see around the industry used for exhaust manifolds, from thin wall stainless, 304 versus 321, just a couple of materials there. There's the thicker wall Schedule 10 steam pipe. There's also mild steel versus stainless. So you've gravitated towards the 321 stainless. Tell us what the pros are with that material.
So the 321 has a higher working temperature range than 304, but honestly, 304 for years, we've never had an issue with either. But the 321, back when it was less available, we reserved it for, road race applications or more endurance stuff where you are wide open throttle for much longer periods of time, where that higher working temperature really pays off. But in recent years, it's been more feasible to get 321 just for everything. So once we were able to do that, we did it. And the cost difference, when you compare it to the amount of time and effort that goes into these, it was kind of a no-brainer just to go step up to the 321 material.
Okay. In terms of that versus the thicker wall steam pipe, I'm just referring to it as steam pipe, but I'm sure most people probably get an idea of what I'm talking about. I see a lot of manifolds made out of that material. Is that material less prone to cracking than a thin wall?
I would say so, yes, especially for like wastegate provisions that are mounted off the collector. Any vibrational stresses the thicker wall stuff, the Schedule 10, which is also what we use, it just holds up better for vibrational issues, and especially like larger turbos and wastegate dump tubes that are acting like vibrating levers, with engine RPM. That's a lot of peace of mind. Just with 321, you kind of have the option to go with a thinner wall, but sticking with Schedule 10 just gives that extra peace of mind because you never want to have to deal with a crack or any issues. And then two, I guess since we're talking about wastegates and vibrations, you'll see on a lot of our stuff we'll tie the wastegate provision into the flange itself, the turbo flange itself, to really anchor it down so it can't have any slight fatigue from vibration, just paying off the collector itself.
I think what's really easy to overlook, and you just touched on it, is the weight of the turbocharger, particularly as you mentioned there with the larger turbochargers. That's a hell of a lot of weight that manifold is supporting. And when you couple that with the heating and cooling, and then all of the vibration and everything else associated with how we use our cars on a racetrack or even on the road, the manifold does lead a pretty hard life. Are you recommending or including any way of bracing or supporting the manifold back to the likes of an engine block to help extend the life expectancy of it?
For a lot of things that we do, bracing really isn't required. And if you do brace it, one of the things you can run into is the manifold's going to move with heat. And if you have a brace that's too constrained, something's got to give. So a lot of times a brace that isn't expanding with the manifold can actually induce other stresses by trying to, stop that natural movement. Where if you want to use a brace, for example, in like a forward-facing setup that, the turbo's out there a ways and you don't want to have all that stress hanging on it, you'd have something like a Heim joint triangulated to just support the weight of the turbo, but still allow some movement and some other coordinates to keep things happy as far as being too constrained.
Yeah, that's the solution I've used on a few of our applications is a rod with a rod end at both ends, Heim joint as you've referred to it, one supported to maybe the engine block off a bracket and then the other to the collector flange or something of that nature. So, I mean, obviously it's still not ideal. The support brace, as I'd refer to it, is not necessarily going to move perfectly with the manifold expansion, but at least it doesn't 100% lock that flange into the same location, which is inevitably going to induce some stresses as that manifold sort of expands, heats up, and tries to move around, correct?
Correct, yeah.
And that is also a technique we see used time and time again on professional sort of built turbocharged race cars. I mean, we've got some photos from an original Formula One car. I think it was the one that Ayrton Senna actually debuted in, and that was back in the original F1 turbo era, of course. And exactly that same, a fabricated triangulated brace with a little link with two rod ends that hangs from that brace down to support the turbo, and that way just obviously helping to support the mass of that turbo as everything moves around and expands. Now, in terms of the fabrication process, I'm interested to dive into that in a little bit of detail. Obviously, you've moved on from the trusty old MIG
Yeah.
and embraced TIG technology. Great. In terms of the machinery you're using, could you give us a little bit of insight into what you've sort of focused on with your business?
So ours is a pretty basic Syncrowave 200. I'll be honest, I don't know a whole lot on that side of things. It's what we've used. It's worked really well, and especially since we're mainly doing stainless. Always using a gas lens. I think that's super important for arc stability or just being able to see the weld puddle, be able to get at least starting off with some consistency for it. I know there's some other things you wanted to talk about for setup.
Well, let's talk about the gas lens and the importance of the gas lens when you're welding a reactive material like stainless steel. Obviously, less of an issue with something like aluminium. But for a start, what is a gas lens? Break that down for us and give us a bit of an understanding.
Yeah, so a gas lens has a few different diffusers in there, and the goal there is to create laminar instead of turbulent flow. So you have a really nice, smooth flow of argon onto the workpiece. you're not introducing any little eddies of like, stray air that would, contaminate the weld or make the metal react. You just want to keep everything ideally with no color change at all while the gas purge is flowing. Allows further stick out.
Yeah, and there's a couple of elements there that are really important. So first of all, again, for those maybe not up to speed with welding, you've got a flow of argon, which is the inert gas that comes through the torch, and you want that inert gas to basically cover the heat affected zone for the weld. And as you mentioned there, a good sign if you haven't got good coverage there is discoloration around the extremities of the weld, right?
Yeah, yep, that's a pretty telltale sign that things might be going awry if you have discoloration happening directly in front of you, which can happen on the regular lens. The non-gas lenses can be, or not lens, but cup can be, really finicky. If you just have a little bit too much gas flow or too little, it's tough. It's best, I think, to just get away from that as soon as you can, just to, have a little less variables, even though there's a ton of variables in TIG welding, but just get rid of at least one of those and get a nice gas lens.
The other thing with the gas lens, the diffusers that they have within them, which, as you mentioned there, sort of stops that turbulent flow that you'd get through the standard ceramic cup and gives you that nice laminar flow. The advantage here as well is you can actually end up reducing your argon usage, if I understand correctly.
Yeah.
Because you don't need to run so much argon.
Yeah, but in our case, we tend to just run a much larger cup and then just, try to just get as much gas coverage as possible so you can get as far of travel as possible. And I definitely see what you're saying, but in our case, like, we're just using a ton of argon in the end anyway.
It's a consumable. It is what it is. All right. You also mentioned that term, the tungsten stick out, and it sort of pretty much explains itself, how far the tungsten sticks out of the torch. Now, you can't get away with increasing that stick out with a conventional cup because you're not going to have good argon coverage around the weld area. And this becomes more important when you're fabricating these intricate manifolds because your access can be very, very tight, correct?
Yeah, even to the point where, a straight tungsten isn't going to be able to get to those areas, or you're not going to be able to get the torch in, especially inside the collector when you're near like the last runner, where you have to have a bent tungsten as much as 90 degrees or more sometimes to direct that arc towards your workpiece. And having that gas lens allows you to keep that weld pool protected, where there's no way you could do that with a standard cup.
Yeah. You just mentioned a bent tungsten, and again, those who are fresh to welding or maybe have had a little bit of experience on a TIG, that's probably a technique that they won't have come across. Sounds a little bit odd. So is it exactly what you're saying there? You simply bend the tungsten and you can weld around a corner?
But yeah, I mean, basically, it's pretty crazy how much you can direct where that arc goes just by which direction the tip of that tungsten's facing. Which is pretty crazy. So, I mean, I can talk you through the process a little bit if you'd like.
Yeah, absolutely. Let's hear it.
So you sharpen it first. That's really important to get it sharp first. And then you run about as much amperage as you can, get it pretty red hot, and then take typically a piece of stainless is okay with a pretty thick piece, and then you just smash it against the side a little bit, and then get it to bend to whatever angle that you need, and that's pretty much it. You just got to get it really red hot, and then you just take the torch and push down at an angle to bend that tungsten over. And
the key there in terms of getting it red hot, making it nice and malleable, easy to bend. And if you tried to just put a tungsten in a vise, grab a pair of pliers and bend it, that's not going to work too well for you, is it?
Yeah, you're going to want safety glasses on because it'll shatter.
Yeah. Okay. Just wanted to sort of focus on that element. You also just mentioned sharpening the tungsten, and this is another element that's really important to getting good quality and consistent, repeatable weld. So what's your process there? And I mean, everyone I talk to sort of has their own sort of theories on what angle to sharpen to, whether they're then leaving it absolutely sharp to a point, or whether they're trimming off the very fine, the very sharp edge. Tell us how you deal with that.
For ours, we tend to use a diamond wheel, just because if you sharpen enough tungsten, it's going to really wear into a standard grinding wheel. So we'll use a diamond wheel. I can't remember the grit right now, but it doesn't leave much for scratches or marks. It's pretty smooth. You want to do it with the direction of the tungsten, so it's kind of pointing at the tip, the scratch lines. We will have a truncated tip where we have a slightly flat end on it, which we found to give more penetration without having to go too crazy with the amperage. It kind of just penetrates further in to get a full penetration on the weld.
So just a bit of experimentation to find what's going to work best for your actual application.
Yeah, and I think the truncated tip has to do with our welder being an inverted welder, and that helps that particular welder get penetration, whereas on some of the newer stuff, you don't need that truncated tip to do that. I'm not 100% sure on that. So
yeah, I mean, I think with the welding industry, with TIG welding, there's a lot of sort of rules of thumb, guidelines, but then everyone also has their own personal preferences or particular processes that they've developed that work for them. So there's sort of some rules of thumb, and then there's a little bit of grey in that area, I think, as well. So, does that sound about right? Is that a good way of explaining it?
Yeah, it's kind of whatever works for you. Experiment, because everything's going to be a little bit different. That's how we just settled on that truncated tip and ran with it.
Yeah. In terms of control for the TIG, you've got the ability to set the current at the machine and then use a switch on the torch, or you can have a variable foot pedal. Variable foot pedal seems to be the choice for anyone fabricating alloy because it requires so much current initially to sort of get the weld pool to form, and because the material is so good at conducting heat away from the weld pool, but then once you've got that weld pool formed, you tend to be able to pull a lot of current out, so the foot pedal is great for that. I mean, not maybe quite so necessary for mild steel and stainless steel. What's your own personal preference? What are you using?
Definitely foot pedal, because you can set the amperage and then you can make it so you can just mat the foot pedal and then just run with it. Typically what we'll do is we'll set it higher than what we need, and then we will modulate the foot pedal depending on if you're starting out, getting that pedal going, and then as you're running along, adding filler, you can adjust on the fly rather than kind of, just having it matted at one spot and trying to work around that. You just keep it really fluid with working with the different conditions and that you're in at the moment, and flexibility.
I guess as well with what you're doing here, you're essentially, I'm assuming, always going to be welding at a bench, which makes the foot pedal kind of a no-brainer. Sometimes if you're sort of wrapped around a roll cage inside of a car, the foot pedal can become a little bit trickier / maybe impossible to use.
Yeah, I've seen some pretty interesting ways of still using one, but there are, I know, some other options, but I've been primarily foot pedals. That's all I can speak to.
Yep, absolutely. All right, the other element I want to talk about is purging or back purging, because again, stainless, it's a reactive material, and we've talked about the fact that we've got that argon flow through the torch and onto the top of the weld, but what's easy to overlook is we've also got a hot molten weld pool on the inside, particularly with these thinner wall stainless tubes, and we need to protect that as well. So what's the process of doing that, and why is it so important?
The process of doing that is to fill the inside. Typically, it's a tube of argon to have it fill. So when you do the weld, you have coverage on each side. That makes it so the inside and the outside look really similar. They're both really clean, no sugaring, and it becomes really important because you don't want any point for a crack to start. And when it starts to have no gas coverage, it has a bunch of sharp edges and nucleation points and stress risers for a crack to start, which I think is one of the biggest things you want to avoid, is anywhere a crack could start.
So reliability is really the key here in terms of the difference. And I mean, fabricated thin wall stainless manifolds, we've sort of alluded to this already, do have maybe a checkered reputation for cracking around the welds, but that's more an element of maybe a manifold that's been subpar in terms of the fabrication processes and hasn't been purged.
That could definitely be a big part of it, for sure. Yeah, lots of things, but just avoid anywhere that would cause a crack to start, and that
Yeah.
back purging is a great place for a crack to start.
Yeah, and again, we don't have the benefit of visuals here, but I mean, if anyone has actually seen the inside of a piece of stainless steel that has been purged versus one that hasn't, generally the one that hasn't, you're going to be seeing a whole lot of sort of, as you mentioned, sugaring is the term, but black ugliness, and you can sort of see how that could be the source of a stress razor and a crack versus back purging. As you mentioned, the inside basically looks almost identical to the outside of the weld, so nice and smooth. I'm guessing there's also an element of improvement in the exhaust gas flow through that, although maybe not the primary concern.
Yeah, when it doesn't have any gas flow on the inside and it sugars, it sticks out a ways. It almost like blooms in the back. So you definitely have something sticking out, protruding into the exhaust flow. So that wouldn't be ideal either.
All right, I want to talk a little bit about the collector design, and these can get quite tricky, quite intricate, particularly on larger cylinder count engines. I mean, obviously we've been talking here primarily about 4-cylinder engines, so we can stick there. In the last maybe 5+ years, I've started to see fabricated collectors. I've seen companies come out with billet merge collectors as well, and then there's also the option of cast collectors. Obviously, the CNC machine billet and the cast gives an easier way of integrating what can be some quite complex shapes and sort of flow paths, which could be a little more difficult to replicate with tube. What's your take on the options there, and what's your personal preferences?
You'll probably notice that we use all fabricated collectors right now, but I'll be honest, the cast and the CNC options are fantastic. When you can use them, I would definitely recommend doing that. For us, we stick with what we have because a lot of the collector angles are really tailored to each manifold design as far as optimizing the angle for the overall height, the wastegate placement. We have, I don't even know off the top of my head how many different style manifolds, and those collectors and the wastegate revisions allow us to really take advantage of all the space available and get the best collector merge angle and transitions as we can. I mean, it'd be possible to go with like a CNC collector, for example, but we have so many different styles that it'd be hard to, account for all of that. It's something we're open to, but right now these are fabricated ones actually work really well for us.
I'm guessing where particularly maybe the cast style comes into its own as well as with high volume production. Going out on a limb, I'm going to assume that a large portion of the time that goes into fabricating the manifold is actually in the fabrication of the collector itself. So if you've got a cast item that you've already had made, that would be a great way of speeding up the manifold production. Am I right there?
Oh yeah, absolutely. It would definitely speed everything up. The collector does take quite a bit of time.
Yeah, but of course, when you're looking at developing a cast product, there's a time investment and obviously a money investment in actually getting those made. So that's the sort of thing I guess that needs to be weighed up. Obviously, though, what you're doing is working well for you at this stage. Let's move on and talk a little bit about heat protection, heat shielding, and this is something that we've run into ourselves on our own endurance car build for a road race application. It's not such an issue maybe on a street car. Certainly we never had any issues with it in a drag race application because the time period that the engine's being used under full power is so brief. But when you're lapping lap after lap for hours on end, the amount of heat that's radiated from the manifold can be a massive consideration to all of the items around it. So, as I see it, the options kind of broadly would be maybe some kind of ceramic coating on the manifold post-fabrication, maybe a conventional heat wrap around the header once it's been made, or going to the extremes of maybe a molded Inconel or stainless heat shielding that's laser welded. We'll see on the likes of maybe professionally built race cars. What's your take on the preference there? Are there any implications in terms of reliability on the header as well?
Yeah, so I'll start with exhaust wrap because it actually does do a really good job of keeping heat in and out of the engine bay. The issue with it though is it's really hard on the metal. it holds in moisture. It can actually, during certain conditions, exceed the working temperature of the metal. And, honestly, on stuff we don't, if it's been exhaust wrapped on a turbo manifold, we no longer warranty it. It's sad that, how well exhaust wrap works for keeping heat where you want it. But coating is a much better option. We're all for coating, keeping some of the heat out. There are certain options that use thicker coatings that have a higher ceramic content that can do something that can rival some of the exhaust wrap. And what's nice too is, it keeps the heat where you want it. And it also helps protect the manifold from the outside oxygen or the outside air, which is what's, attacking it once it's at those really high working temperatures. So you get kind of the best of both by keeping the harmful oxygen, I guess, away from it, and then, keeping the heat where it should be as well. We don't have any personal experience with the Inconel heat shielding, but we do have quite a few setups out there that are running it, and it does seem like a great option, especially since I think they have a slight air gap between the manifold and the heat shields. The manifold's allowed to breathe a little bit more and not, put it under so much abuse where a wrapped exhaust header would.
Sure. Interesting. You mentioned the wrap. Essentially, you don't warranty it, and that's what I've sort of heard from a lot of manifold suppliers. Shame when it actually does work quite well, but that's the situation. In terms of the ceramic coatings, I've personally sort of seen variable results, and I mean maybe it's just the suppliers we have access to here in New Zealand, particularly around the coating discoloring at the elevated temperatures we see in turbo manifolds. Is that purely just around the product being used, and there are reliable solutions out there?
We have seen some that hold up really well even after many years of use, but that's something we kind of more so leave to the customer themselves instead of us trying to figure out the coating and having, a little more experience personally, firsthand experience. So I've seen plenty work out fantastic. I've definitely seen some that flake off very quickly.
Yep.
So,
all right. One of the last questions I wanted to ask you about is in terms of fasteners for turbo applications. And in my own experience, I've sort of had or seen mixed results here in terms of fasteners working their way loose, and this is more particularly around the interface between the exhaust manifold and the turbocharger as well. In more recent years, obviously V-band exhaust housings have become a lot more prominent, which really kind of makes that problem go away. But yeah, what's your take on that? I mean, there's solutions that include high temperature locking nuts. I've also seen the likes of the Nordlock washers, the serrated washers that sort of lock in. One of my own personal preferences on the T25 style, the smaller flange turbochargers, Nissan actually have a factory locking tab mechanism. It's a mechanical lock that you put on the flange before you put the nuts on. Then once the nuts are on and tightened, then you actually physically bend the tab up against the side of the nut, which makes it impossible for them to work loose. There's the full gamut there. But yeah, what's your sort of take on it?
It actually isn't an issue that we really run into much, but we have heard really great things as far as like the Nordlock or locking washers to keep things in place. More so what we've been more concerned about is some people will, for example, our flanges are stainless, threaded stainless. When people use a stainless bolt, stainless on stainless tends to gall up when you go to take it back out. So that'd be the opposite issue. So we actually go with just a high grade bolt, making sure it's a dissimilar metal, so that way when you do go to disassemble it, you're not, stripping out any threads. But as far as things vibrating loose, I'm sure it can happen, but not something I can speak to quite as much.
The dissimilar metal point is a good one as well, because there is nothing worse than trying to remove a stud and having a stainless bolt or stud. Normally what's going to happen is it'll gall up, as you mentioned, and you obviously keep applying force to it, and at some point it then just shears off, and then you're left with the unenviable task of trying to extract a stainless stud out of a hole, which never really, it's a good way to ruin your day in my experience. So yeah, good point that you raised there, Matt. Look, we want to probably move on here, and I'll get on towards wrapping this thing up, Matt, and let you get out of here. We're we appreciate your time and want to respect that. So we've got the same 3 questions that we ask all of our guests. The first of those is, what's next for you and your business in the future? What's on the horizon? Any changes that you can share with us?
Mainly just try to keep doing some more testing, keep trying to figure things out, and offer some new products. There's constantly new things, new applications, people coming to us. We really stick with just EVOs and DSMs, but there's always a plethora of different new combinations that we'll develop and then get up on the website and offer. So just continuing on and, keep doing the testing, and honestly probably try to get tech articles out there to kind of share some of the things we've learned during our testing would be a big thing too. Get back to that.
Obviously, just on that note, I mean, the Mitsubishi market, no big surprise there. We're not seeing any Evos come out anymore. So I'm guessing that means it's going to, at some point, become a diminishing market for you. A lot of the Evo guys from the time that I was involved ended up jumping ship onto the GTR platform. Is that one that you've got your sights set on, or is there any specific platform that you think is going to be the next big thing for you?
I mean, we're so heavily involved and have so many close friends. I don't know. I think we've just been so lucky to have so many people coming to us where this is it, So, I mean, we'll cross that bridge when we get to it. I'm sure it's going to eventually get there, but it seems like the people who are in it are really in it and doing some really cool stuff and coming to us, and we're really grateful for that.
Yeah, I definitely don't think that the community is going to die anytime soon. As you mentioned, there's a die-hard contingent there of Mitsubishi fans, and I probably count myself among those anyway. All right, next question. Given your experience in the industry, where you've got to in your career, if there's any advice maybe that you could give to a younger version of yourself, maybe one of our listeners out there who's wanting to sort of follow a similar career path, any advice that you could give to maybe fast track that career or maybe avoid any pitfalls that you've come across yourself?
I think interest is the best way to gain new knowledge, and you're really taking advantage of that. And two, I guess you never know what other life experiences will be beneficial down the line, and what you do end up doing, and try to utilize all of that and apply it in what you do end up doing.
I think that the passion side of things is really important. I've said this a number of times in episodes before, but it does bear repeating. Is trying to do something that you genuinely are passionate about is, in my opinion, just so important. And obviously, we've got to tempt that with something that can actually put enough money in your pocket to be able to make a living out of. But if you could enjoy your day-to-day work, then all power to you. It's a situation that many people aren't in, and I think that's really unfortunate. A last question for today, Matt. If people want to follow your journey, see what you're up to, reach out, maybe buy your products, how are they best to do so? You've got some social media channels, your website, etc.
Yeah, the website is morrisonfabrications.com. You can find us on Facebook, and Instagram is Morrison Fab. Always trying to post up pictures of customer projects we got going on and stuff going out the door all over the world. So
perfect. Well, we'll put some links in the show notes to those accounts to make them nice and easy to find. Look, Matt, it's been great learning a little bit more about your business and about the design and construction of manifolds. Keep up the good work, and we appreciate your time.
Yeah, thanks so much.
If you enjoyed this episode of Tuned In with Matt Morrison, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt anywhere in the world, free of charge. Also, this is a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to John W. from Canada, who's said, incredibly technical show for car nerds. I would say 90% of automotive podcasts are basic discussions of new car releases, how they drive, and drama. The technical aspect of this podcast is in a lane of its own in the podcast format. I feel like I'm browsing an old car forum with how detailed and technical the discussions are, with true expert guests in whatever the topic of discussion is. This is the first podcast review I've left, but this one deserves it. really scratches an itch for people into this type of thing. Keep up the great content. Oh, really glad to hear you're enjoying the podcast, John, and keep listening because we've got some more great content coming up. In the meantime, if you get in touch with your t-shirt size and shipping details, we'll fire a fresh tee right out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.